Hi, and welcome to Week 12 Mini Lecture 1 for the Quantum Universe for Educators. In this lecture, we're going to pave the way to discussing quantum entanglement by talking a little bit about how to represent two-particle systems in quantum mechanics. Up to this point, we have generally only dealt with the possible states and wave functions of single particles. Now, when dealing with quantum entanglement, we're dealing with, in its simplest form, two-particle systems, such as, for example, two electrons that get produced when two high-energy photons collide. Because the photons have zero spin, then by conservation of angular momentum, the spins of the two electrons must also add up to zero. So therefore, if one has spin up, the other has spin down. If one has spin down, the other has spin up. And we describe this, the state of the two electrons, with a wave function that looks like this. Okay, so this is a superposition state like we've seen before, but now each part of the wave function refers to the states of two particles at once. So this first part here refers to the first electron having spin up and the second spin down, and the second part of the wave function refers to the first electron having spin down and the second having spin up. And in quantum mechanics, if we haven't observed the system, then the state of these two particles is a superposition of both of these states. Now, the minus sign here comes in because of a property of electrons that we will explore in a couple of weeks' time. So at the moment, just take the minus sign as given. Okay, so this is an example of an entangled state, and we'll talk more about conceptually what an entangled state is in the second lecture. Firstly, let me note that sometimes you can represent this state in a slightly more compact way by writing a ket plus minus, where the first entry refers to electron 1 and the second to electron 2, and the same for the second part of the wave function. Sometimes you'll see the state written like this. We, however, will generally explicitly write the kets of both particles. Now, the labels on these kets tell you which electron we're talking about. So the subscript 1 here tells you that this ket refers to electron 1, and the subscript 2 tells you the ket refers to electron 2. These kets behave just like the single particle kets we've already seen. So they're inner products of plus with plus and minus with minus, and plus with minus and minus with plus give 1 and 0 respectively, so long as the kets refer to the same particle. Right. So they hold for electron 1, and they also hold here for electron 2. But the inner product of a ket state with a bra state which refers to a different electron is always 0. Okay, even if it's the inner product of plus with plus and minus with minus. With that information, we can check that this entangled state is properly normalized. So taking the inner product of this state with itself, then the bra version of the state is given here. And that's multiplying the ket version of the state. Multiplying out these brackets, you get 4 terms. The inner product of plus with plus for electron 1 minus minus with electron 2, the inner product of plus with minus for electron 1 and minus with plus for electron 2, the inner product of minus with plus for electron 1 and plus with minus for electron 2, and the inner product of minus with minus for electron 1 and plus with plus for electron 2. The first and last of these terms are equal to 1, and the second and third are equal to 0. So overall, we get the answer 1. So the state is correctly normalized. The other thing we have to notice is when we have two particles, when we write down the spin operators that represent the observables, then we have to specify which electron they're going to operate on. So the spin operator for the spin in the z direction for electron 1 is called S1z, and the spin operator for electron 2 is S2z. So for example, if S2z operates on a piece of wave function that looks like this, so you have a plus ket for electron 1 and a minus ket for electron 2, then S2z doesn't care about electron 1's ket. and it just passes straight through it and only acts on electron 2's ket. Since electron 2 is in the state minus, so spin down, then when you operate on that state with the spin operator, you measure a spin of minus h bar divided by 2. That is the magnitude of spin when it's down. So the overall result, you can pull this factor of minus h bar over 2 back out past electron 1's ket because it's just a constant, and you get that this is equal to minus h bar over 2 times the state that we started out with. And as a final reminder, something that is worth checking, and this will come up on a homework problem, a state such as this is an eigenstate or an eigenvector of a spin operator if the spin operator acting on that state gives you a constant times that same state, with a constant being the possible result of a spin measurement. So in this case, it will be plus or minus h bar over 2. So if you want to figure out whether this entangled state is an eigenfunction of a spin operator, then you have to act on this state here with one of the spin operators and see what you get.